What if we told you that one of the world's coldest countries is igniting the hottest breakthroughs for a better tomorrow? VTT, the home of deep tech solutions and over 50 spin-off companies, drives positive impact on the biggest challenges of our time. We can help bridge the gap between innovation and commercialization, overcoming the valley of death. As your trusted partner, we bring together brilliant minds, advanced research infrastructure, and cutting-edge technology. Together, we can turn bold ideas into a better future. VTT, your visionary research, development, and innovation partner.
So good afternoon, ladies and gentlemen. My name is Mika Härkönen, and I will give a presentation together with my colleague Ugur Kaija about VTT and especially what we are doing with mechanical recycling, developing higher quality products. So now you have opportunity to take a picture of this QR code and then give questions, send questions during the presentation. We will try to then answer those after the presentation. I guess you have got the picture. So, back to the heading slide. So, I don't know how many people know what is the picture behind here. And this even doesn't tell where we come from. So we actually come from VTT, the Technical Research Center of Finland. And this is Helsinki, our capital, during night time. So we are a research center, a technology organization that is developing technologies and helping industry to turn science into innovations. So we are working in applied research. As said, we are also developing own technologies. We are creating IPR for licensing, and that's one way to also accelerate the technology development. But we are also providing services like scale-up services for industry to scale up their own technologies. We are also doing science because we have to keep our excellence in good level, so we are also writing scientific articles. So that's the role of VTT in the innovation chain. In plastic recycling, we have been working quite a long time already. I don't know if you have ever seen this picture, but this was made already 6 years ago. It was about vision, how we see the future, probably quite many years ahead, about circular economy of plastics. I would like to take 3 things out from here. One is that you see a lot of circles. So as we know, there is not only one solution. It has to be parallel solutions to really solve the plastic challenge. And then you see the orange part of this picture. That is the current linear industry and value chain. So all these circular technologies should be some kind of drop-in solutions to existing industry and infra, because that only makes it really feasible and possible to materialize. And the third thing I would like to take out is that we believe, even though this presentation is about mechanical recycling, but we also believe that the kind of feedstock recycling, chemical recycling, bio-based feedstock, and even carbon dioxide feedstock will play a notably bigger role in future. But probably it will take some decades before we are there. So then about a little bit closer vision. So we see that there will be a combination of mechanical recycling and chemical recycling, and probably also solvent-based recycling in between, and energy use for plastic waste. All three are needed. And the sorting will be a key role. How do you sort? Probably you will sort differently for mechanical recycling than chemical recycling. And I have a background from plastics industry, so I would say that the biggest difference between mechanical recycling and chemical recycling is the product. They are used for different purposes, different applications, and the product is different. And also the development needs are different. I mean, mechanical recycling, as you will hear today, the focus is to really create better quality and cost-effective solutions by sorting, blending, compounding, product quality in the compounding phase. And then, of course, one important thing is the food contact grade for polyolefins that are not really existing today. In chemical recycling, there's different kind of target research topics, and as said, the chemical recycled plastic is needed when you need a equal to new quality. But the other topics are like increased yield, lower carbon footprint, access and use of low cost accessible feedstock. And then I would say a very important part is to increase the capacity. Really the production capacities of chemical recycling units are far too low today in order to get some kind of economy of scale. So VTT Research Institute, we are developing different things, but of course we are not looking for something that is ready maybe today. We have a little bit longer perspective, and that means that we are looking for how to recycle plastics and industrial feasible high capacity processes, and then of course higher quality plastics. And in addition to recycling, we are also promoting other ways of circular economy, like reuse, design for recycling. And we are working with all these fields, so design for recycling and also use of recycle is one topic. We can utilize our experience and equipment. Pre-treatment is a topic we have put in lot of focus now. It will be a new capabilities on sorting and washing. Ugur will tell more about those. Mechanical recycling also a very important part, and those two are the focus of today. Then we are also doing pretty much work with the chemical recycling, pyrolysis, higher yield, lower quality, cheaper feedstock. Gasification is interesting because it every now and then pops up. But of course, if you go to synthesis gas route, the main strength of that you don't have to sort your feedstock. But it's still not maybe mature enough for implementing. So even though this is about mechanical recycling, I will just show one research example of chemical recycling, what we have been doing, and it was announced early last year that we have sold a exclusive license to an American startup company, Refinity, that is owned by a venture capitalist, so they have money. And now, of course, this is something we are developing together with them and also Dow to the next stages. This is a good example for our research, but also maybe not that good example for European industry, because we were discussing, with all European big companies, but nobody had the kind of capability to take the risk to scale up, and then we found an American US company. But that's quite often the case. Anyhow, I think I now leave the stage to Ugur to tell about our mechanical recycling.
Thank you, Mika. Thank you very much, Mika. Good afternoon, everyone. We all would like to enable the recycled contents and increase the recycled content in our products, but usually the problems are the inconsistency of the products, impurities, and contamination levels. For this, we all need to increase the sorting, washing, reprocessing, upgrading capabilities to enable higher-end applications. And as VTT, we are aiming to close the gap between the industry and research with the line of these capabilities. And I would like to introduce some of these to you. Before moving on to our pre-treatment and washing capabilities, I would like to introduce you our sustainability assessment tool and plastics compass. So this is a three-step process from criteria definition and piloting to the piloted solutions. Together with our research partners and our customers, we first identify the sustainability criteria. What are they really desiring in their products? What are the most important things? The end properties, and for example, the availability of the feedstock and many criteria. And then we pick some of these alternatives and we screen these properties in the second stage. And we have many prototypes in the very small scale. And this typically takes 3 to 5 months. And then what we really do is to go into the verification stage, where we prototype a few of these alternatives. And at the end, you don't only have the ideas in your mind, but you also have the prototypes that are actualized. And you are able to pick one of these ideas to commercialize. And moving on to our new capabilities for plastic waste pretreatment, I would like to start with the advanced identification and sorting line. So this is a flexible platform that we are currently working on, and we are aiming to enable the usage of several different cameras, sensors, sensor fusion capabilities, and we would like to, for example, detect foreign materials in the plastic or textile feedstock. It can be food contamination, water or battery contents, battery contamination, or for example, you will be able to detect the multi-layer structures, multi-layer packaging materials, for example. And also, what will be possible here is to adapt new detection methods, because the line will be flexible, different than the commercial ones. So we will be able to test different detection and sorting strategies here, together with the AI fusion and AI models and sensor fusion capabilities. So the next stage is the pilot-scale intelligent washing of the plastic waste. This will also be a modular line with the capacity of 100 to 200 kilograms per hour throughput. And it will have a separate big shredder, and we will be able to adapt wet and dry washing, wet and dry granulation, wet and dry friction, and float sink tanks, centrifugal dryer, mechanical dryer, thermal dryers, and bagging stations. Hot and cold washing will also be possible with this line. It will be also possible to skip some of these modules because it's a really long line, or if you would like to repeat some of the stages, it will also be possible. And we will also adapt sensors and data logging for research needs. This will also be let's say, filling the gap, a tool for filling the gap between the lab scale washing and industrial washing lines. I think we believe that it is highly needed in European infrastructure. So I would like to introduce you our high-quality plastic recyclate processing through inline controlled extrusion capabilities here. We have developed an advanced mechanical recycling line equipped with the state-of-the-art inline property monitoring tools. So what we are really aiming here is to transform the extrusion from black box into a data-driven processing capability. So you will be able to understand what's really happening during extrusion and compounding. And I will explain you a bit more in detail. So when you have your recycled feedstock, I think many of us know here is that we might have very different levels of fluctuations in our feedstock. You might have multi-layer, multi-material components. You will have polymeric impurities as well as non-polymeric impurities. You might have a polypropylene, but you might end up with some PET inside. And you might have hazardous additives, for instance, legacy flame retardants or PFAS. And of course, you have your fluctuation of your properties in the feedstock within the batch or between the batches. So with these inline measurement technologies, we are aiming to monitor all of these properties continuously and teaching our line to give the possibility to the line to decide itself how to behave and how to react during the extrusion and to adapt the extrusion parameters. So going a bit more in depth into our advanced mechanic recycling line. So we are, of course, melting and melt filter the recycled plastics, and we have inline rheology measurement capabilities. So you will be able to measure your viscosity or MFIs continuously during the extrusion compounding. And this is also supported with inline spectroscopy capabilities, and these include UV visible spectroscopy, where you can derive, for example, RGB by coloring capabilities. And then there will be NIR, near infrared sensor, which is able to monitor the contaminations of other polymers, for instance, or VOC, volatile organic compounds that you can monitor the gas outputs. And we are also able to upgrade and homogenize the feedstock to reach a virgin-like material quality with the support of all of these tools. So this is an open piloting platform open to all of our partners, from research to industry. We are happy to collaborate with you in this line. But going a bit more technical, what we really do here is we first feed the plastic waste feedstock to a single screw extruder. And here we have the possibility to feed a little bit more bulky structures than just granulates. It can be flakes or a little bit larger parts like films or a little bit textiles. And then it goes through melt filtration. Then we measure the viscosity inline continuously, as I mentioned before. And then all the melt is fed to the twin screw extruder, where really the compounding happens. There we are able to feed additives, virgin materials, or several other, for example, polymers that we would like to blend with our main polymer. And then towards the end of this twin screw extrusion, we also monitor the rheology again. So we have double viscosity values before and after the actual compounding. And these, we also have the sensors for, as I mentioned, the UV visible spectroscopy, near infrared and VOC analysis adapt to this line. And these are all connected to VTT's in-house developed software controller for the rheological monitoring. So the machine will have the possibility to decide itself from which component to feed to reach a desired viscosity level. So you first teach the equipment with the materials properties. So you run the extrusion, and then the material or blend models are taught, and then the machine will have the own decision capability for feeding. So how rheology controlled extrusion process work? So this, where we first collect the learning data. If you have a waste feedstock, the equipment will be run for how many hours that you would like to have, 6 hours, 24 hours, maybe a few hours only. And then you will get a few different material blend ratios. So the equipment is taught with virgin and waste feedstock blends, you can, for example, have 80-20 virgin waste feedstock ratios, and then you have 60-40, 50-50, 30-70, and then the equipment gathers all the data. And all of these data is fit into a multi-material empirical mixing model. And then you have these nice curves, 3D curves there, where you have the possibility of the effect of different feed ratios at different levels. And then you set the desired target viscosity profile at several shear and elongational rates, and you are free to choose and user-defined approach. And then inline adaptive control of material feeding to reach user-defined target viscosity profile is enabled. So if you would like to reach 10 MFI of a polypropylene, but it's fluctuating between 8 to 15, then you first teach the data, teach the material to the equipment, and you have your other additives, other polymers with the same chemical composition, but with different MFI levels. So the equipment will tell you how much that you should add to reach a certain viscosity level. And with the inline spectroscopy, advanced process control, from the melt state, we have UV spectroscopy. So you get the melt state color, LAB colors, heterogeneity and dispersion monitoring possibility, and you are also able to watch the stability and degradation, for example, from an indicator like yellowness, or you understand the effect of additives, and residence time analysis is also possible here. With the near-infrared spectroscopy, you go more in depth into the chemical composition. So if you have another polymer type that you don't want in your polymer stream, but you don't know the feedstock either, the exact composition of the feedstock, you run the extrusion, and then if you come up with PET composition at some point, it will be shown in the log, for example, in a PP compound. And you will also be able to monitor the chemical reactions if you have reactive extrusion, compatibilization, or other types of reactive extrusions. And you will see heterogeneity, again, stability and degradation. They will be complemented with the UV-vis, and of course, effect of additives. With the FTIR spectroscopy, we are able to detect volatile organic compounds by qualitative and quantitative means. And we have developed an in-house solution for sampling for vacuum degassing line. And I also would like to highlight here that we are working with our partners, Colvistec and Gasmet, for these sensor solutions to adapt to our extrusion lines. So what are the key benefits of inline quality monitoring? Just to have an overview, you are able to have a real-time analysis because you have a comprehensive data sets, collected data set that is directly from the process during the compounding, what's really happening. You are diving into what's really happening. And you also reach to a batch-specific material quality statistics. Imagine you have multiple batches from your supplier, and they are produced at different times, and they have different logs. But you're able to distinguish the properties of these different batches. But what really happens is that we can also diminish the property differences within the batches and between different batches. And of course, it will help you to reduce the off-spec waste generation. And with the direct monitoring of critical quality attributes, if you have a certain end product resin, then you will be able to see the viscosity MFI values directly at the same time without going to the offline rheological measurements. And you also see homogeneity if there is any foreign particles or any foreign polymer impurities. So this will improve the material and processing safety and sustainability, because safety is also one part of recycling. When you think about, you are dealing with usually unknown compounds, or you might have unknown compounds and surprises in your process. It also helps process optimization, so real-time measurement of processing property relationships and residence time distribution. For instance, this is possible. And you can also see the effect of the extruder, screw design, and extrusion process parameters on the fly while you are doing the compounding. And of course, at the end, you enable the smart process control. So rheology and spectroscopy controlled extrusion using a data-driven model-based approach will enable you to act more smartly, decrease your R&D time, and also increase your consistency in your production. Let's have an overview of what we have talked today about VTT's capabilities. So we have an open platform, a piloting platform for circular plastics covering most of the areas. As Mika also mentioned, chemical recycling and several other recycling technologies. But starting with a pilot-scale intelligent washing line for optimized pretreatment, which will be effective by 2027. We are also going in more detail with advanced detection and sorting platform. And this will be a test platform, as I mentioned before. So we would like to enable different sorting techniques that are not existing conventionally with our new sensor fusion and AI-based models. And with the adaptive extrusion process control, we would like to increase the inline quality and enable the consistent and high-quality recyclates to reach virgin-like properties. With the design for circularity plastic compass tool, we would like to start with the design for recycling from the material design and prototype, and also provide the sustainability assessment for improved recyclability at the end of the day. With pilot scale pyrolysis, gasification, and chemolysis routes, we also aim to convert hard to recycle plastics into high quality, high-end applications. And of course, all of these happen with product development, process optimization, and scale-up support for our industrial recycling technologies and companies. Thank you very much. So maybe we can have the tablet. Yeah.
Yes, we have some questions here. And more questions. We have a booth actually here. It's an N48, just other end of the hall. But of course, there's some questions, and we can answer what we can. I think I can take the first one, which was about the hard to recycle plastics. Are they phased out because of the design for recycling? Of course, they will hopefully decrease, but I think there will be still. You need some multi-layer structures. You need some barriers, and maybe also some plastic waste are mixtures of different plastics, and maybe all sorting is not always possible. But of course, that is true that it is. Hopefully, they are decreasing. But still, maybe it's not about how hard to recycle, but what is the kind of cost of the feedstock. Then maybe you can take the second one.
Yeah. So the second question is about, can your new washing lines be contracted for research purposes? Additionally, are there various types of washing lines, different OEMs? Yes, it will be possible to probably contract the washing lines, of course, within the certain agreements, and we would like to, of course, work with the industry like OEMs, brand owners, but also not limited to that. Any recyclers, resin producers, we are open to discover this area as well. Medical waste.
And the second part was that the various type of washing lines, and as Ugo said, it's a modular system. There can be different kind of washing, starting from dry washing for chemical recycling down to the food grade washing purposes. Then decontamination methods for medical waste. This is topic we have been working to some extent, and that would there be methods that they don't need to incinerate the medical and pharma sector? The plastics there are quite, there's a lot of packaging plastics in medical that are today incinerated. So there could be methodologies to sort and if needed also to autoclave or disinfect somehow. And I think that's a very, it's not very, well, it's relatively big waste that is incinerated today, and this is already on our agenda. What about other degrees?
Yeah. Yes, exactly. VOCs are not directly related with the odor, so we don't have a sensor dedicated to the odor, but we are indirectly working with odor with the VOC. But this is a field that we are also looking into, but we don't have a sensor dedicated for the odor right now. But we just have the capability to have the odor removal as well from certain plastics, and this is a very good question actually. So thank you very much. I think we are over with the time, and please feel free to visit our booth as well at N48, and have a great rest of the exhibition. Thank you.
Okay, thank you.
What if we told you that one of the world's coldest countries is igniting the hottest breakthroughs for a better tomorrow? VTT, the home of deep tech solutions and over 50 spin-off companies, drives positive impact on the biggest challenges of our time. We can help bridge the gap between innovation and commercialization, overcoming the valley of death. As your trusted partner, we bring together brilliant minds, advanced research infrastructure, and cutting-edge technology. Together, we can turn bold ideas into a better future. VTT, your visionary research, development, and innovation partner.